Okay, today's lesson is converting between graphs and equations to graphs. So we're going to start with going from an equation to a graph, and there's a couple of things that you want to pause and take down. And again, your notes are getting a lot better. Just anything that I've said or anything that you want to ask, I would do it in a different colored pen. So remember that equations for linear for lines are in slope-intercept form, which is the y equals mx plus b. Your b represents the y-intercept, which is where your line is going to intersect the y-axis. The coefficient of x then is the slope. It's the rate of change, which is rise over run, which is delta y over delta x, lots of different things. So when you're given equations like example 1 and example 2, in order to graph them, you can follow this little algorithm here. So first we want you to plot your y-intercept. Then you're going to use the slope to plot the next 2 points to the right, because remember, just like in English, we work left to right. Connect with the straight edge always, because anything that doesn't have a context, that isn't a word problem, is going to be continuous, because x could in fact be anything along that line. So if you're just given something like this, there is no context to it, go ahead and connect it with the straight edge. So if I'm telling you to graph example 1 and example 2, beware, because example 2, look how they flip-flop it around. It's not in standard form, so you want to really make sure that you understand that the constant, no matter where it is your y-intercept, since that's the very first thing that we're going to plot. So you could do 2 separate graphs, or you can strategically construct a scale that's going to include both of these. So that's what I'm going to try on my graph paper, and we are focusing on a high quality graph. So this one starts below and then it increases. This one starts up and then it's going to decrease.
So it looks like if I were to construct my y-axis, make sure you label it y, and then we'll put the x maybe somewhere here-ish. All right, make sure you label it x, and again you have arrowheads in both. With the first one, let's color code them. So line 1 we're going to say is blue, and line 2 we'll put in red. Because if you're going to put 2 lines on one particular graph, you need to somewhat have a key. So if I'm telling you, with example 1, to first plot the y-intercept, well, we have to figure out what our scale is, because without a scale, a graph means nothing. You don't have to label every single line here, but you do have to give us some sort of reference tick marks. I'm going to say that I'm going to label every 2 as 2, 4, 6, and the same thing on the y. They don't have to be exactly the same, but it has to be consistent within the axis. So I'll go here, and then sure, I'll come like this. So if I'm going to plot the y-intercept for example 1 in blue, it's going to cross the y-axis down at -2. So first I plot the y-intercept, and then it says use slope to plot the next 2 points to the right. So slope says I go up 5 and right 4. So from here, literally, I'm going 1, 2, 3, 4, 5. 1, 2, 3, 4. I'm going to put another one right there. If it says to do it twice, I'm just going to follow directions. 1, 2, 3, 4, 5. I barely made it. 1, 2, 3, 4. And then I can go ahead and connect these with the straight edge because it is continuous. X could very well have been anything. Put some arrowheads here and here. And there's the graph for example 1. Example 2 is a reverse situation. It has a positive y-intercept, so we're going to plot the y-intercept here at 3, and then a negative slope means that as we read it left to right, it's going to decrease. So what this is telling you to do, if the coefficient is a -1/2, remember the law of science tells us that we put the negative with the top. So this means from this particular intercept, I'm going to fall 1 and then run 2. So my triangle is going to look like this. Fall 1, run 2, there's a point. Fall 1, run 2, there's a point. And if all I have to do is make 2 to the right, then I'm going to go ahead and connect it with a straight edge. And there are your 2 lines. So example 1 is increasing at a rate of 5/4. Example 2 is decreasing at a rate of 1/2. So positive slope and negative slope.
So now you go ahead and try it now, and you graph y equals -2/3 x minus 1. Okay, so we're going to take this and we're going to put a different colored marking, and we're going to try to put it on the same graph. So I'm going to say this is in purple. You should have put the intercept at -1, so you have a point right here. And then the line is going to decrease 2 and then run 3. So decrease 2, run 3 means you have a point here. Decrease 2, run 3, you have a point here. And you're going to connect it with the straight edge. So you have a point that goes like this. So now we're going to talk about going the reverse situation. So what if we were asked to write an equation from a graph? So here's sort of what you want to follow for this scenario. You want to look at your line and you want to identify at least 2 lattice points, meaning 2 lines that are on an intersection, a grid on your paper. And then you're going to calculate the slope between those points. And then if the y-intercept is not obvious or not shown on your graph, you need to be able to solve for that algebraically. So example 3 and example 4, we've made you these examples now. And we're going to try to do these together, making an equation in slope-intercept form. So with these 2 graphs, this is continuous data. They should have arrowheads here and here, here and here, and on the x-axis and the y-axis also. So for these to be high-quality graph, we want to make sure to do that every single time, like so. And then we can go ahead and think. We need an intercept and we need a slope. So the first thing that I had you do is scan this line, and we're going to try to find at least 2 points that are on a lattice point. So we work left to right. If we're looking, it's not going to happen. It looks like it happens here. So I'm going to put a point right there. Keep going, keep going, keep going. It looks like it's going to happen here. Keep going, keep going, keep going, here. And all we really need is 2. And any points along this line, it'll work for. So one point that we need to be aware of is where this line is hitting the y-axis. And it looks like it's happening right here at -1. So what does this refer to? It's the intercept, which in our equation is b. So we have that the intercept is b. Now we need to figure out what the slope is. This line is increasing from left to right, so we know it has to be positive. So there's a couple ways you can solve for slope. If I'm already given a graph, I like to use the slope triangle method. So what that means is I'm going to take the 2 closest points together. I start with the left point, I work my way to the right. How do I get there by rising? Well, I create this little slope triangle like this. So it looks like I go up 1, 2, 3. That's a rise of a +3. And it looks like I run 1, 2. That's a run of a +2. So this slope is a rise of 3 and a run of 2. So it has a slope of 3/2. So stringing this together as an equation, y equals mx plus b, we just found that the slope is 3/2, so it's going to go in for the coefficient. And then we just said that the b, the y-intercept, is a -1, so we're just going to say that's -1. So the equation for that particular line is y equals 3/2 x minus 1. You can verify that by the same thing. If I took this lattice point, which is the ordered pair -2, -4, I plug in -2 here, I plug in -4 for the y, this should balance out. So if you wanted to check it, 3/2 times -2, make it look like a fraction, minus 1 should in fact give me a -4. So if I simplify the right side, I have 2 on the top, 2 on the bottom. That's a -1. We got a -3 minus 4. -3 minus 1 is a -4. So there's another way to just test to see if your equation is correct. Okay? This guy, example 4, is going to decrease as we go left to right. So if you look at this very carefully, we want to identify our lattice points, and you realize that it is not crossing the y-axis at a lattice point. So what this means is we're going to have to solve algebraically for what our b is. So we scan this thing and we're looking for lattice points. It looks like it happens here, looks like it happens here, here, and again all we need is 2. Looks like it happens here, and probably somewhere down here. So first we got to figure out what our slope is and then work our way backwards to our b value. So the slope, start at the left point, go to the right. From here I go down 1, and then I run 1, 2, 3 in this direction. So again, with the slope triangle, if your line is decreasing, notice that it's going to be below the line versus the previous example when it was increasing, it's going to be above the line because I do rise before I run. You get out of bed in the morning before you run out the door. So in this case, we have a slope of -1/3. So now that we have the slope, we have to figure out where exactly the line is touching that y-axis. So algebraically, we have to think what to do to solve for b. So we know that the slope is negative 1/3, so we plug that in for m, which is the coefficient of x, and then we have some options. We can use any point within this line to plug in an x value and its corresponding y value. I'm going to use the very first point here, which is, let's see, -7, and then that looks like a +3. Or if I didn't want to deal with negatives, I can go to this guy here and think, well, this is 8, but then I have to go down 2, so that one's dealing with one less negative. I'm going to see perhaps if there's anything that has an x value of 3, because what I'm going to do is multiply the x value by -1/3, so if I can maybe get a multiple of 3, I could do some cross simplifying here. So it might not work, but that's okay. It's possible that b is not a whole number, which we know because it's not quite on it's not quite on these points here. So we'll choose the original one here. So x is -7, so I'm going to plug it in here. Its corresponding y is +3, so I'm going to plug it in here. And then I'm going to algebraically solve for b. So I do the math like so. A negative times a negative is a positive. I can't cross simplify. That's a +7/3 plus b is equal to 3. How do I isolate b? I get it by itself. Well, I have to SPO 7/3 minus 7/3 makes that 0 minus 7/3. There's a couple ways you can do this. If I'm going to get like denominators, and this guy is how many thirds? Well, he's 9/3 minus 7/3 gives me 2/3, and it looks like b is 2/3. So if that is reasonable, we'll go ahead and look up here. 2/3, is it between 0 and 1? Well, yes, and algebraically that should work out. So when you put it all together in one equation, you think y is equal to the slope of -1/3 times x plus the b value of 2/3, which we just found algebraically. So again, your line crosses the y-axis on a point that is not quite on one of these lines, you're going to have to do this process and solve for b. Okay? So now you go ahead and try these on your own. And here are your two equations, and I want you to write the equations for the lines. So I'll zoom in a little bit, think about the process, and then go ahead. So on A, you see that you're looking for lattice points. You could have chosen this guy here, and then keep going. It looks like this one, it looks like this one. So your intercept is b is 2, and then the slope triangle is going to be below it. So from here to here, I access it by going down 4 over 1. So your slope is a -4/1, or simply a -4. So when you put those two together, we have y is equal to -4x plus, well actually, plus 2. Okay? And if you check it and it doesn't work, then that just tells you that we have found something that wasn't quite a lattice point. Okay? On B, we have an intercept that looks like it's at -3. And then I have a point that's here. If I were to do a slope triangle, that means you go up 3 and then you run 3. So we have a slope of 3 over 3, which is 1. And so when I put that in my equation, I don't really say y equals 1x. I simply say x, and then its intercept is down at -3. So I say x minus 3. Okay? Now we have a couple of special cases with some graphs here. Our special cases, our special lines, you kind of visualize in a bunch of different ways. But just understand that anytime we read a graph, we read it left to right. So if you're going to envision someone skiing this particular path, as you go left from right to right, this is positive, so you think he's going up the hill. It's positive, he's puffing up the hill, puff, puff, positive. Then he gets to the top and he reverses direction. So then he's going to ski down this and he's like, nice, it's negative. Nice. And then he gets to this area right here, and then he's like, well, this is kind of 0 fun for us. 0, fine. And then he hits this wall, and it's impossible to ski up this wall. So when this happens and you hit a line that is like this vertically, you call that undefined. And we're going to take a look at why that is so. So with our special cases, you have, of course, slope is change in y over change in x. If we have a horizontal line, our slope is 0. If we have a vertical line, our slope is undefined. The reason being is because if you think of the components of slope, if I have a change in y that is 0, 0 is your top, it's your dividend. If you have a change in x, if this is a reverse situation, and you have 0 on the bottom, let's make up a number for the other. Say it's 12, and then the reciprocal of this. 0 divided by 12 is 0. If you don't have any change in the y-axis, if I have 0 and I divide it into 12 groups, each group has 0. However, if you look at this scenario, if I have 12 people and I divide them into 0 groups, that's impossible to do. You cannot divide by 0. So when the change in x is 0, when it's on the bottom, you say that the slope is undefined. Okay. These are not the same thing. 0 is different from undefined. Here are the two graphs to look at now. In example 5, here are my two special cases at work. I have a graph that is completely horizontal, and you think, if I were to come up with an equation here, if x is 2, look at this point here. If x is 2, y is 2. Pick another point. If x is 8, y is still 2. So x is changing, but y remains the same. There is no change in y. So my rise, in fact, is 0. If you were to come up with the equation for this line, no matter what I put in for x, y is still 0. So the equation for this special case horizontal line is y equals 2. It does have an intercept at 2. It's just perpetually stuck there forever. So y equals 2 is this horizontal line with what kind of slope? 0 slope. You think slope dude is having 0 fun. You can think of this being a horizon and the sun is coming up over the horizon like a big old 0, whatever it takes you to remember this. Example 6, we're going to put something maybe right here. And I'm going to put in a vertical line like so. And in our slope dude analogy, he's hitting a wall. It's impossible to go over this wall, so it's undefined slope. It is impossible to divide by 0. Therefore, 0 is my denominator. And what's the denominator? Well, that's your run, your change in x. So if this happens, it is undefined. So we think about what this means. And if I look at this point, the coordinates of this point is 5, 6. If I go down and I look at this point, the coordinates of that is 5, 2. So what's happening is that x isn't changing. X is still 5. So there's absolutely no change along the x. If you wanted to think about this further, y could be anything and it's 0. If you were to think about maybe this being time, so at any particular hour, at the 5th hour, say, so hour 5, and maybe this is like the distance from Grandma's house, and you're going home for Thanksgiving from Granny's house. What this line is saying is that at the 5th hour, you are 6 miles away, and you are 2 miles away at the same exact time. So this cannot exist in reality. This is undefined. You cannot divide by 0. So our two special cases is a horizontal line where there's 0 slope and an undefined slope when there's a vertical line. This equation is sort of going to be like this guy, except it has x perpetually stuck at something. So the equation for a vertical line, we think, if this was my line, my equation is x is equal to 5. Forever and ever and ever. So you look at the two, our special cases, normally we have equations that have a y and an x somewhere in them. These two are special. So if y is stuck at 2, it's a horizontal line. If x is stuck at 5, it's a vertical line.